So where we stopped off yesterday is we go ahead and we created these three lines using the patty paper. If you'll go ahead and put it in your journal. So when we did the inverse, what we should have noticed is that it was a folded over the line y equals x. And it's a reflection over that line. And this is the line y equals x. Anytime you have a function and an inverse, they are always going to be reflected over that line y equals x. So if I gave you 0.32 on the original graph, let's say 1 over 3 up 2, on the new one, it would become 2, 3. If a given point in the graph of the original is -1, 0, then the new point is going to be -0, -1. So anytime you have an inverse, all we're doing is we're switching the x value, so whatever your x value might be, and your y value in their locations. So if it was originally AB, it becomes BA. So now let's do the same thing, but now for the quadratic graph. So I want you to take and use your patty paper and trace this. Now fold over the line y equals x, which is this line here. And then trace the image. You should have ended up with your graph looking something like this. So remember when something is a function, so the question number 2 asks us why is the inverse, which is what's in blue, not a function? And that's because it fails the vertical line test. So of the function, the domain and range of the function, domain was from -infinity to +infinity, or all reals. And the range was from 0 to +infinity, or you could have written it as y is greater than or equal to 0. For the inverse, the domain now starts at 0 and ends at +infinity. Or again, you could have done it, but this time it'd be x is greater than or equal to 0. And the range, that was domain, is all reals. So it will eventually cover all the reals. And that's the -infinity to +infinity as an interval notation. So if you'll notice, the domain and range switch locations on inverse functions. And so now let's go ahead and go through and solve the equation and solve for the new function. So when we're doing this, step 1 is going to replace the y the f of x with that y. Now we're going to trade locations. So the x is going to replace y, and the y is going to replace x. And that gives you to your step 2. And then you solve for y. So that means we need to take the square root of both sides. And so when we take the square root, remember we have to always do the plus or minus. And so that's a new equation. But this is not an inverse because there's that choice. Because there's that plus or minus. Because that plus or minus is not the inverse, is not a function. So we can take and restrict the domain and range in order to create the inverse. So if I was to create the domain and range, let's go ahead and go with this, the square root of x. So that's this part right here. Our range is from 0 to infinity. And our domain is from 0 to positive infinity. And we talked about that when we do the restricted, or when we do a domain and range, they are going to switch places. And it really didn't change anything on this one. But let's take the negative square root of x. So our domain, again, is from 0 to positive infinity. But our range goes from negative infinity, because it's all the lower stuff. So it goes all the way up, and it stops at 0. So, and if you look at it on that original piece, that domain goes from negative infinity and stops at 0. And our range is at 0 to positive infinity. So it always is going to take and be where the domain and range trade for the inverse. And when we restrict the domain, that's going to get it to where we have a function. So if I was to take and do the restrictions here, then this right here, that portion is a function. And so do all of these graphs up here, if I was just to have it restricted, do they all make a function? Yes. Because each of these are functions. And we already knew these two were functions. So with those restrictions, we're able to take and create functions. Okay, so Marissa is competing for the A drop competition in their science fair. It is required to create a container, which they place the egg in, and they're going to drop it. She knows, based upon formulas, that she's dropping it from 64 feet. And so she knows the function is the half the speed of gravity in feet squared plus your starting point, 64. So my independent is my input, remember. My output is my dependent. And so what we're plugging in is the time, and the output is the height. And so my input is x, which is my time. My dependent, or my output, is the height, which is my y. So based upon this equation, what is my domain and range? Well, just on this equation here, without any other information, my domain is all reals. My range is all positive numbers for y. So that means that if we were to do the inverse, we're going to have to take and restrict it. And so we can restrict the domain. So the restriction will need to be x is greater than or equal to 0, because we're only worried about positive time anyways. And so that's what's going to make sense in this problem story. So let's go ahead and graph with the restrictions based upon this problem situation. Let's go ahead and do that. And so I'm only worried about that first quadrant. And so I'm starting off at 64, and I'm going to count by 16ths. 1, 16, 32, 48, 64. Actually, I'm going to do a little bit more than that. Let's count by 4s. And so every 2 is going to be 8. And so I know that at the start, I'm at 64 feet. And I'm going to count by quarters on time. 1, 2, 3, 4. That gives me 1. 1, 2, 3, 4. That gives me 2. And if I plug in and solve this to find out where it crosses the x-axis, so 0 is equal to negative 16 x squared plus 64. And again, remember, I'm only worried about the positives. I just want to figure out where it crosses the x-axis. So negative 64 is equal to negative 16 x squared divided by negative 16. And that gives us 4 is equal to x squared. And when I take the square root of that, I have plus and minus 2. Again, we're only worried about the positives. So that's where it's crossing the x-axis. And so I'm just going to sketch in that graph. And so that's based upon the restrictions. It's going to continue to go down because we don't have to worry about where it's ending. Now, if ground level happens to be here, we're not going to be worried about what happens underneath the time. But if we're sitting on a cliff, then we might need to worry about what happens later. So, and we're going to go ahead, and the next thing is we're going to restrict the domain. We're going to go ahead and, based upon our restrictions, draw the inverse. Oh, and so therefore, the independent, our plug-in, is going to be time, and our output is going to be the height. So when we do that, the graph is going to reverse to where this is 2 and this is 64. So what is the domain and range of the inverse with the restricted domain? So remember, I'm still going forever that way. And so x is less than or equal to 64. I am stopping here for the range. And so y is greater than or equal to 0. And so when we restrict the domain of the first, then the equation is going to create an inverse function. And so we restricted it to the positive x values. And so when we take the square root, we're only going to use that positive sign. And so remember, the function was f of x is equal to negative 16x squared plus 64. So first step is going to make this y equals negative 16x squared plus 64. We're going to trade those two places. And so it becomes x equals negative 16y squared plus 64. And so we're going to try to undo those operations. So we're going to move the 64 over. And so x minus 64 is equal to negative 16y squared. Next step is going to be divided by negative 16. And so y is equal to, y squared is equal to x minus 64 divided by a negative 16. Now I've got to undo the squared. So you're just going to take the square root of both sides. And so without the restriction, it'd be plus and minus. But since we have that restricted to just the positive, it's just going to be the positive of it. So this becomes our new function. It's the inverse function of x. And you put this little negative 1 here to show this inverse function. X minus 64 divided by negative 16. And so this models an inverse based upon the problem situation because we have that restricted domain. And so what this does is we now can take and use either one and figure out which one would be the best one. So if we know the time, then we want to go with the original function because we want to plug in time to get the output. So f of x is equal to negative 16 1.5 squared plus 64. And then we can find out that the value of that is 28. So we're at 28 feet off the ground. But if we were wanting to take and plug in feet and get time, then we need to use the inverse. So we're going to use the f negative 1 of x is equal to the square root of 64 minus x divided by a negative 16. Excuse me. I think I just wrote that backwards on the previous problem. Yes, I did. X minus 64 divided by negative 16. And so I can plug in that 55 feet minus 64 divided by negative 16 into my function, and that will give me 3/4 or 75 hundredths of a second. Since we're trying to find the time, that's the most efficient way of going about it. So if you're trying to find out if it's a one-to-one function, actually we'll pause here. If it's a one-to-one function, both the function and its inverse are going to be functions. And so I want you to go ahead and sketch the graph of the function using the solid line, then graph the inverse. And then I want you to try to come up with the equation of the inverse and determine if it is a one-to-one. So in other words, are both the original and the inverse functions. This is your homework for tonight. And so y'all are going to go through and do each of these problems. We will discuss them at the start of class tomorrow. If you finish that, start on Mathia, the inverse unit, which is, so Mathia, Unit 10.